Hello, welcome back to this lecture series on quantum chemistry. In this lecture, I am going to continue the particle on a sphere of fixed radius. Okay, in the last lecture, I have derived the expression for energy and wave function for a particle on sphere of fixed radius. Today, as in this lecture, I am going to discuss few more informations on energy and wave functions. Okay, yeah, let me start energy first. So energy of particle moving on a sphere of constant radius. Okay, and I have told you on the sphere the potential energy of the particle is assumed to be 0. Therefore, the total energy here is nothing but rotational kinetic energy of the particle. Okay, and it is quantized, which is given by the expression L equal to h square by 8 pi square I into L plus 1. Okay, where L is the quantum number which can take values 0, 1, 2, 3, 4, etc. Okay, and you can also write this h square by 8 pi square I. It is a constant for a given particle, and that constant is represented as B. So B into L plus 1. Okay, where B is called rotational constant. In the last lecture itself, I have told you it is called rotational constant. It is a constant for a given particle. Okay, then for a given value of L, okay, suppose if some value of L is given, L equal maybe 1, 2, 3, 4, etc. For a given value of L, there are 2L plus 1 possible values of ML exist. Okay, what are the possible values of ML? ML value can go from minus L through 0 to plus L. Okay, these things we know. Now, listen, in particle on a sphere, we have two quantum numbers L and ML, but energy depends only on the quantum number L only. Okay, it depends only on quantum number L. Right now, okay, suppose if I plot these energies in the increasing order, how the energy will exist. Okay, what will be the energy spectrum? Okay, let me show that here. Yeah, so this is energy axis. Okay, the lowest possible value of L is 0. If L is 0, then the rotational kinetic energy becomes 0. If L is equal to 0, the rotational kinetic energy for the ground level is also 0. Okay, so it you know very well, for rotational kinetic energy, the classical lowest value for rotational kinetic energy through classical mechanics is 0, and through quantum mechanics also 0. Therefore, 0 point energy is 0 here. That means there is no 0 point energy. Okay, that means there is no 0 point energy for particle and a ring system. Okay, similarly, we had already discussed that there is no 0 point energy for particle and a ring also. Okay, keep that in mind. Now, suppose if you put L equal to 1, okay, you will get here 1, you put 1 here, 1 plus 1, 2, so 2 times B you will get. Okay, I'll use this expression. 1 plus 1 is 2, so you will get 2B, right? So next energy is E1, which is equal to 2B. Okay, but for L is equal to 1, 3 possible values of ML will exist. Okay, therefore, for each possible value of ML, we have a state. So for L equal to plus 1, ML plus 1 may exist. For L equal to plus 1, ML 0 is another possible value. Then for L equal to 1, ML minus 1 is another possible value. For all these values, see, L value is same. L value is same. You know very well, energy depends only on L value. Therefore, for all the 3 states, energy stays same, but ML values are different. Okay, therefore, these 3 states have different wave functions. Okay, but they have same energy. So we can say that these three are degenerate states. So degeneracy of this level is 3. And the general formula for degeneracy is 2L plus 1. For a given value of L, we have 2L plus 1 possible values of ML. This is nothing but degeneracy. Now, if I put L equal to 2, what will I get? Put 2 here and 2 here. 2 plus 1, 3. 3 into 2, 6. So you will get 6B. So the next level, which is E2, when L equal to 2, you will get the energy as 6B. Okay. For L equal to 2, we have 5 possible states. 5 possible states exist. What are the 5 possible states? L equal to 2, ML plus 2, L equal to 2, ML plus 1, L equal to 2, ML 0, L equal to 2, ML minus 1, and L equal to 2, ML minus 2. Okay, so we have 5 states. So degeneracy for this level is 5. Is 5. Okay, so ground level degeneracy is 1, also called non-degenerate level. First exit level is triply degenerate. Second exit level is having a degeneracy of 5. Like that, as you go above and above, you will get the degeneracy increases in the case of particle and a ring. Keep this in mind. In the case of particle and a ring system, except the ground level, all other levels are doubly degenerate. Whereas in the case of particle and a sphere, except the ground level, as we go to the higher level, right, degeneracy keeps on increases. Okay, that's the point you should note. Then another point is, listen, the gap between the ground level and the first exit level is 2B. 2B minus 0, it is 2B. And the gap between the first exit level and the second exit level, 6B minus 2B is 4B. So as you go and above, see the gap also increases, right? So the energy gap between adjacent level increases as L increases. As the quantum number L increases, okay, the gap between adjacent level also increases. So this is another notable point we should keep in mind. Okay, this is regarding energy for rotational kinetic energy for a particle moving on a sphere of constant radius. Okay, and here let me make this. Let me tell you this point again. Here we are here total energy represent rotational kinetic energy of the particle. Okay, because we assume the potential is just 0, right? And the rotational kinetic energy does not have continuous value. It has only quantized values. Okay, there is a gap between one level and the other level, and another level. There is a gap. That gap indicates that the energy levels are quantized. Okay, yeah. So this is regarding energy. Now I'll come to the wave function. The wave function for particle on a sphere is also called as spherical harmonics. So we will discuss about spherical harmonics. Spherical harmonics. This is O, which is represented by the symbol Y, which depends on the quantum number L and the quantum number M, which depends on the variables theta and phi. Okay, and you know, in the last lecture I have given the expression for Y as square root of 2L plus 1 by 4 pi into L minus modulus of M factorial divided by L plus modulus of M factorial times the associated Legendre polynomial PL of M. Let me put x here. Remember, x is nothing but cos theta into e power I ml into phi. This is also ml. Right. So this is the wave function formula. Now let me start with the lowest level. What is the lowest level? The lowest energy level where L equal to 0 and ML also 0. So this is actually 0, 0 state. Okay. What is the wave function for 0, 0 state? So L equal to 0. If L is 0, the only possible value of ML is 0, which means, or it represents the wave function L0, ML0, theta phi. So this is the wave function for the ground state. Okay. Now, this is a way we represent what is the wave function. For this, you have to use this formula. First, let me find out the associated Legendre polynomial. To find associated Legendre polynomial, first we should calculate the Legendre polynomial. What is Legendre polynomial? PL of x. PL of x equal to 1 by 2 power L into L factorial into d by dx whole power L into x square minus 1 power L. This is the formula. So here we should put P L value is 0 here. P 0 of x equal to, wherever L is there you put 0. So 2 power 0 is 1, 0 factorial is 1. So this become 1. D by dx whole power 0, 1. X square minus 1 power 0, that is also 1. So here the Legendre polynomial value is 0. Remember, whenever m is 0, then associated Legendre polynomial is equal to the Legendre polynomial. Both are equal. This is associated Legendre polynomial. This is Legendre polynomial. These two are equal. Okay, when ml equal to 0. So in our case, ml is 0. Therefore, these two are equal. So this is also equal to the Legendre polynomial, associated Legendre polynomial P 0 0 x. Legendre polynomial, associated Legendre polynomial are one and the same. I'm sorry, 1 into 1 into 1, 1. Yeah. These two are same whenever ml is 0. Okay. So this is the value of associated Legendre polynomial. Now I'll substitute this value here. So wave function y 0 of 0, L 0, ml value 0, which depends on the function theta and phi. Yeah, let me calculate this. If I put L equal 0 here, 0, so you get 1 by 4 pi. Okay, L0, M0, 0 minus 0 is 0, 0 factorial is 1. Similarly, 0 plus 0, 0 factorial is 1. Okay, so this becomes 1. And the Legendre polynomial value is 1 for the ground state. And if I put ml equal to 0 here, e power 0 is 1. So this is also 1. So I am getting a value which is nothing but 1 by square root of 4 pi. So this is the wave function. Let me write here. Wave function for the ground state, okay, is 1 by square root of 4 pi. It is a constant. It is a constant, and see in this expression there is no theta and phi. So this is independent of, this function is independent of theta and phi variable. It does not depend on theta as well as phi. Okay, yeah. So now how to represent this function or how the function will actually exist. Right? Let me show you to the next page. In a graphical manner, I will show that. Yeah, how this function will exist in space. Right? So let me just draw in a 2D plane. So let us take this is the z-axis and this is the x-axis. Okay. Now, see, this is a constant, right? Suppose this constant has some value here. If you change the value of theta or if you change the value of phi, right, this constant doesn't going to change because the function is independent of theta and phi. Therefore, you'll get the same value around the circle. Okay, you'll get the same value everywhere. So the function will look like a hollow circle, a hollow sphere. Okay, it is a hollow sphere. So the wave function for the ground state, because it is independent of theta and phi, so whatever value of phi, whatever value of theta, okay, theta will increase from plus z to minus z. Then phi value will go from plus x to, then it will go to 360 degree and once again comes to plus x. Okay. So since the function is independent of theta and phi, right, and it is a constant, therefore the values should be same everywhere from the origin. Okay. This is possible only if the function will appear like a sphere. Okay. So the ground state wave function will appear like a hollow sphere. Hollow sphere. This is how the wave function will look like for the ground state, okay, of particle on a sphere. Now let me go to the next level, that is the first excited level, where L equal to 1. If L equal to 1, the possible values of ML are 0, plus 1 and minus 1. Okay, first let me take L equal to 1 and ML equal to 0. L equal to 1 and ML equal to 0. How this function will look like, right? So first let me find, so which means we need to find out the function L1 ML value 0 theta phi. This is the function we need to find out. Okay, to find this, what we should do? First we should calculate the Legendre polynomial P1, L value is 1, P1 of x. Okay, what is the value of Legendre polynomial? See, here we have the formula. The formula is 1 by 2 power L into L factorial d by dx power L x square minus 1 power L. Wherever L is there, you put L equal to 1 now. So 2 power 1 is 2, L factorial is 1 factorial is 1, d by dx power 1, x square minus 1 power 1 will be getting. Okay, so I will get 1 by 2 power 1 into 1 factorial into d by dx whole power 1, then x square minus 1 power 1. Okay, that means you have to differentiate this ones. So 1 factorial is 1, so this become 1 by 2. If I differentiate this, I will get x square. X square on differentiation will give 2x, 2 cancel, so we will get x. And here ML is 0. I told you when ML is 0, associated Legendre polynomial and Legendre polynomial are one and the same. So P1 of 0 of x is equal to x. Okay, and you know very well, x is nothing but cos theta. Okay, x is nothing but cos theta. Right, now let me go to the function y1 0 theta phi equal to, okay, what is the normalization constant? So this is the formula. First put L equal to 1 here, 2 into 1 2, 2 plus 1 3, so you will get 3 by 4 pi here, 3 by 4 pi. Here 1 minus 0 factorial is 1 minus 0 is 1, so 1 factorial is 1. 1 plus 0 is 1, 1 factorial is 1, so this will give you 1. Therefore, I will get square root of 3 by 4 pi here, square root of 3 by 4 pi into, and associated Legendre polynomial value is cos theta. Okay, and if you put ML equals 0 here, e power 0 is 1, so that term vanishes. Okay, that term become 1, I'm sorry, e power 0 is 1, so that term you need not write. So this is the wave function for L equal to 1 and ML equal to 0 state. Okay, and how does this function look like? See, this function depends on theta. It is independent of phi. It is independent of phi. So how does this function look like? Let me show it in the next page. Yeah. So if I plot this function, let us take this as x-axis and this is z-axis. Okay, this square root of 3 by 4 pi will have some value. Okay, when theta is 0 degree, cos 0 is 1. 1 into square root of 3 by 4 pi is square root of 3 by 4 pi. Assume that this value is somewhere here. Okay, along z-axis, because theta 0 degree means along z-axis. Then as you move away, theta value increases, right? For cos 30 degree, cos 30 is 1 by 2, so 0.5 times this. So for cos 30 you will get point somewhere here. Then cos 45 is 1 by root 2, 1 by root 2 into this, yes, you will get the point somewhere here. Okay, then cos 60 you will get the point somewhere here. Then if I put theta 90, cos 90 is 0. So you will get a semicircle, right? It almost looks like a semicircle. Right, when you move from 0 theta, right, I am varying theta from 0 to 90 degree. From 0 to 90 degree, I will get a semicircle like this. Then if I increase the angle from 90 to 180, I will get another semicircle which go in the negative direction. Right, now listen, here we have drawn, or we have plotted this theta value, or we have plotted this function, okay, along this x-axis. Okay, that means we have taken phi equal to 0 degree here. Along x-axis means phi equal to 0. Now since this function is independent of phi, whatever may be the value of phi, okay, this is, suppose assume that this is y-axis, right? Now I am going to rotate. If you move away, okay, phi value increases. If this is positive x, phi value increases. When you come to the same point, the total phi angle becomes 360 degree. Okay, since this function is independent of phi, whatever phi angle you take, you will get same type of semicircle above and semicircle below. So if you rotate this in 360 degree, you will get many number of loops like this, many number of loops. Okay, so if you draw all the loops, the loops will appear something like this. Okay, the loops will appear something like this, right? You will get a hollow dumbbell along z-axis. You will get a hollow dumbbell, right, along z-axis. This is not a pz orbital, but it appears like pz. Okay, but pz orbital is fully filled, right? It's a fully filled or filled with electron cloud. But here this orbital or this function appear like pz orbital, but it is not pz actually. It is a hollow dumbbell. Okay, yeah. So the state L equal to 1, ML equal to 0 appears like a hollow dumbbell, okay, which is lying along the z-axis, right? Similarly, if I take the next one, P, I will take L equal to 1, ML equal to plus 1. If I take L equal to 1 and ML equal to plus 1, how the function will look like? So this represents the function L1 ML plus 1 theta phi. Okay, so PL of L value is 1, so P1 of x we need to find out. This value we have already calculated. P1 of x is we already calculated, which is nothing but x. Okay, but ML value is plus 1 now, so associated Legendre polynomial will be different. So what is the associated Legendre polynomial? P1, here we should take modulus, so P1 of 1 of x equal to, what is the formula? The formula is this, 1 minus x square into modulus of m by 2, so I will get 1 by 2 here. Okay, I will get 1 by 2 into d by dx power modulus of m into the Legendre polynomial, which is x. Okay, and ML value is 1 here, so let me put 1 here, right? So I will get root of 1 minus x square, differential of x is 1, root of 1 minus x square, x is cos theta, so 1 minus cos square theta is sin square theta, root of sin square theta is sin theta. So associated Legendre polynomial is equal to sin theta for L equal to 1 and ML equal to plus 1. Therefore, the function y L1 ML plus 1 theta of phi is appears like square root of, I will use the formula. In this formula, I will put L equal to 1 here. So I will get 3 by 4 pi here. Now L equal to 1, M also 1. 1 minus 1, 0, 0 factorial is 1. So numerator is 1. Denominator L equal to 1. Modulus of M is also 1. So 1 plus 1 is 2. 2 factorial is 2. So I will get 1 by 2 here. Here I will get 3 by 4 pi. Here I will get 1 by 2. So 2 into 4 is 8 pi. So I will get square root of 3 by 8 pi here into associated Legendre polynomial is sin theta, and e power I, ML value is plus 1. So e power I phi you will get. Okay. So this is the wave function for L equal to 1 and ML equal to plus 1. Since we have a complex function here, we cannot plot this function as such. Okay. Yeah, I will keep this function as such. Then let me check with L equal to 1 and ML equal to minus 1. Okay. Then if L1 ML minus 1 also appear with the complex function, then you can take linear combination of these two. Okay. So what I am saying is that say that suppose I'll take the function C. What is C? L equal to 1, ML equal to minus 1, which represents the function L1 M minus 1 theta phi. Okay, how to find this? We should find out P1 of x. P1 of x is x only. Okay, and P1 modulus of M. Listen, ML value is minus 1, but modulus of ML is 1. Okay, so that is also equal to sin theta. That doesn't change. Okay, this is also equal to sin theta. And what about the function y1 of minus 1 of theta phi? Equal to, you will get the same 3 by 8 pi, because the normalization constant, you are going to take modulus of ML only. Modulus of ML is 1. Okay, so this value remains same, into associated Legendre polynomial is sin theta, into e power, here ML is minus 1, so you will get e power minus I phi. Okay, now see this function and this function. These two functions, they have same energy, right? Because L value is 1, here also L value is 1. You know very well, energy depends only on the quantum number L. So these two states have same energy, but since they have complex function, you can take a linear combination of these two functions. Linear combination will give new two functions. You can represent those functions, okay, or you can consider those functions as the functions of these states. Okay, so what I am trying to say is that I am going to take linear combination of these two. So y1 plus 1 plus y1 minus 1. I am taking linear combination of these two functions. Okay, linear combination. Addition will give one linear combination and subtraction will give another linear combination. Okay, which is equal to, we should add a normalization constant. Since we are adding two functions, assume that the two functions contribute equally. Therefore, the coefficients of each function should be 1 by root 2, 1 by root 2. Okay, so the normalization constant is 1 by root 2 into, and in each of these two functions, root of 3 by 8 pi, here also we have root of 3 by 8 pi, here we have sin theta, here also we have sin theta. So these two are common for these two functions. So I will take it out. So if I take those two out, square root of 3 by 8 pi into sin theta, then we left with e power plus I phi in the first one and e power minus I phi in the second function. Okay, e power I phi is nothing but cos theta plus cos phi plus I sin phi. This is cos phi minus I sin phi. So this is cos phi plus I into sin phi, Euler's theorem. And this is cos phi minus I sin phi. And adding, these two cancel. So cos phi plus cos phi, you will get 2 cos phi. So you will get 2 by root 2 square root of 3 by 8 pi into sin theta into cos phi. Okay. If you bring this 2 inside square root, it becomes 4. 8 into 2 becomes 16. 4 by 16 becomes square root of 3 by 4 pi. So you will get 3 by 4 pi, square root of 3 by 4 pi into sin theta into cos phi. Okay. So this linear combination will give you a function, right? And see, you know, in the spherical polar coordinate, I have told you x is equal to r cos theta, y is equal to r sin theta cos phi, okay, and z is equal to r sin theta sin phi. I'm sorry, made a mistake. This is x, this is y, and z equal to r cos theta. Okay, so this is up here like, see, it has sin theta and cos phi. Sin theta into cos phi is there. Therefore, this is something similar to px function. It is not px orbital. Okay, it has a function. That function look like x. Okay, x in spherical polar coordinate. So let me represent this as some function, say this linear combination behaves as px function. Let me give same symbol y px. Okay, y px. The linear combination addition will give a new function. And remember, if you plot this function in xyz coordinate space, you will get a dumbbell, hollow dumbbell along x-axis. Okay, you will get a hollow dumbbell. Suppose I will take this as x-axis, then you will get a hollow dumbbell, right? Remember, this is hollow. Okay, you will get a hollow dumbbell along x-axis. So that's why I have given this symbol as px. It looks like a px orbital, but it is not px orbital. Okay, because px orbital, it is not a hollow dumbbell. It is actually a dumbbell filled with electron cloud, whereas this is a hollow dumbbell. Okay. Similarly, subtraction will give another function. Okay, let me subtract these two. So we do it here. If I subtract these two functions, y1 plus 1 minus y1 minus 1, subtraction, if you subtract, you will get minus cos phi here, and this become plus I sin phi. If you add, I will get 2i cos phi cancel, and you will get 2i sin phi. So I will be there. To remove I, okay, I am introducing the normalization constant like this, I into root 2. So this is the normalization constant for the addition of these two functions, into, and root of 3 by 4 pi sin theta, root of 3 by 4 pi sin theta is common for those two functions. So I will take the common terms, 3 by 4 pi into sin theta. Okay, then we have e power plus I phi minus e power minus I phi. Okay, on adding these two, you will get, I'll keep this I as such, 1 by root 2, and here we have root 3 by 4 pi. I'll keep sin theta as such. Subtraction will give me 2i sin phi. Okay, right? So this I cancel. Then 2 by root 2, root 3 by 4 pi on simplification will give square root of 3 by 4 pi. So this is 3 by 8 pi. Yeah. Okay, the function as square root of 3 by 8 pi in both the y1 plus 1, y1 minus 1. So if I take common, if I take the common term, I will get square root of 3 by 8 pi into sin theta. And if you simplify this, okay, bring this 2 inside, you will get 4 into 3, 12. If you multiply these two, you will get 16. So 12 by 16 will give me 3 by 4 pi into sin theta into sin phi. See, sin theta sin phi in spherical harmonics, sin theta sin phi is similar to y. Okay, so this function, right, will give me a new function which appears like py function, right, which appears like py orbital in the case of hydrogen atom, right, but it is not orbital actually. It is a hollow dumbbell appear along y-axis. Okay, so if I take this as, this is x-axis, this is y, and this is z, so you will get a hollow dumbbell, right, which appears right along. So hollow dumbbell, you will get a hollow dumbbell which appears along y-axis. Hollow dumbbell. In YouTube, lot of videos are there for the three-dimensional pictorial representation of these functions, right? So if you want, just go through the YouTube channels and find out and try to understand, okay, how this function actually look like in three-dimensional space. Okay, so here I have I'm just make you to understand these functions will appear like a hollow dumbbell. Okay, but if you want to view this function in 3D space, okay, better you go to some YouTube channels, YouTube lectures, and you can find it out. Okay, how the functions actually look like. Okay, yeah. Similarly, if I go to the next level, L equal to 2, in L equal to 2, we have ML value plus 2, plus 1, 0, minus 1, minus 2. ML 0 will give you D is a square like function. D is a square like function. Okay, listen. Let me give this point. I am not going to discuss. If I take L equal to, I will get possible values of ML. ML 0, ML plus 1, ML minus 1, ML plus 2, ML minus 2. See, L2 ML0 will give me a function which appears like T is a square orbital. Okay, and the linear combination of L equal to 2 ML plus 1, L equal to ML minus 1, okay, will give me two new functions of d orbital, maybe dxy or dyz like that. Similarly, the linear combination of these two will give another two d orbital functions. Okay, when L equal to 2, these functions will give me a three-dimensional shape which appears like d orbitals, but they are not d orbitals, they are hollow double like shapes. Okay, yeah. So keep all these things in mind. This is regarding spherical harmonic part of particle and a ring system. Okay, before completing this, let me give one more information and then stop. Listen, these associated legendary polynomials, they are all orthogonal functions. Okay, so in the limit minus 1 to plus 1, okay, I will take two functions y, L, m, theta, phi. This is one spherical harmonic function, and y, instead of L, I will put some value n, m, theta, phi into d theta into d phi, d theta into d phi. Okay, two states may be orthogonal or may be normalized, or if L and N are same, okay, you will get a normalized function. Okay, since the functions are normalized, you will get the value as 1. Sorry, you will get some value. If the two functions if L and N are different, okay, the two functions are orthogonal. See, what I am trying to say is that this value should be equal to, let me write here, should be equal to 2 by 2L plus 1 into L plus m modulus of m factorial divided by L minus modulus of m factorial, okay, times the Kronecker delta of L and n. Okay, this is the value of this integral. If L equal to n, then the Kronecker delta value delta Ln should be equal to 1. If L is not equal to n, then the Kronecker delta value is 0. So accordingly, the function will get different values. Okay, so actually I made a mistake. I'm sorry. I should take associated legendary polynomial. Sorry, P L of m. Sorry, let me write. I made a mistake actually. Yeah, integral minus 1 to plus 1 P L of m x into P, instead of L I will put n, Pn of m x, associated legendary polynomial functions, right, must be orthogonal, okay, if L and n are different, right, into dx equal to this value is 2 by 2L plus 1 into L plus m factorial over L minus m factorial into delta Ln. Right, this is the value of the product of these two associated Legendre functions. Listen, this is a very useful function because using this you can find whether the two functions are orthogonal or not. Okay, you can check it by using this. Right, keep this information in mind, very important. And here this is Kronecker delta value, and you know very well Kronecker delta Ln will take two possible values, either 0 or 1. When you will get 0? If L is not equal to n, then you will get 0. If this is 0, the entire quantity becomes 0. It means the two functions are orthogonal to each other. Okay. If L is equal to n, that means the two are same. If the two functions are same, since it is normalized function, you will get the normalization constant value. You will get some value. That value is equal to this quantity. Okay. Yeah. So keep this information in mind. This is very, very useful. Okay. Yes. With this, we have completed particle on a sphere model. In the next lecture, I am sorry, actually I left one thing, that is I left the angular momentum part of this particle on a sphere. Okay, we will discuss the angular momentum part in the next lecture. Okay, once we complete the angular momentum part of particle on a ring system, then I will start hydrogen atom problem. Okay, yeah. I stop here. Thank you for listening.